Again, here we're still talking about the Lorenz equations, and we discussed some of their simplest properties in the last lecture. Today I want to get into some of their more complicated properties, in particular the possibility of chaos in the Lorenz system. And but before we do get to that, I want to finish up with one thing that we left from last time, which is we said that when this parameter r, that was the Rayleigh number, was less than 1, I claimed that all trajectories would asymptotically approach the origin. And we don't have any techniques for showing something like that, at least not yet. And so I want to show you a method for proving global results. So, as I say, every trajectory approaches the origin as t goes to infinity. If the damping is sufficiently high. So in that sense, we say the origin is globally stable. That's as opposed to locally stable, which we already showed using linearization for r less than 1. But what that means in particular, if the origin is globally stable, it means since everything's going to the origin, they are not going to stable limit cycles or chaos or anything else. There are no other attractors. So no limit cycles, strange attractors, or anything else. For this case of r less than 1. Now, to prove it, this is sort of a sketch of the proof. We're going to define a function v of x, y, z that, let me just write the function down and then tell you what's so powerful about it. Here it is, 1 over sigma x squared plus y squared plus z squared. And where did I come up with this function? Well, it's not at all obvious. There's great art in coming up with one of these functions. This is an example of what's called a Lyapunov function. And you can think of it this way. It's analogous to an energy function in a system with dissipation or damping, friction. That is, you know, if you had a classical mechanical system and you wrote down the total energy, but then there was friction, then that energy would keep decreasing monotonically as you were losing energy to dissipation. And that's what we want this function v to be like. It's going to be a function that will monotonically decrease over time. And because of that, we're going to be able to prove that that implies that x, y, z have to approach the origin. So this is an example of a Lyapunov function. So it's as I say, an energy like, not strictly speaking an energy here, but it's something that's sort of like an energy in a system with friction. It keeps decreasing along trajectories. That is, it keeps going to smaller and smaller values as time goes on. So let's think about this geometrically just for a second. If you look at this function v, it's almost a sum of squares, just x squared plus y squared plus z squared, except for this factor 1 over sigma. If it were just x squared plus y squared plus z squared, then when v is a constant, a positive constant, that would define the surface of a sphere in x, y, z space. As it is, though, with this parameter sigma in here, level sets of this are ellipsoids. So they are actually concentric ellipsoids, and they're centered at the origin. So let's draw a little sketch of what they're like. You know, roughly speaking, it looks sort of like this. So there's one ellipsoid, and then, you know, so it's supposed to look three-dimensional. And then if you went down to a lower value of v, there'd be some other ellipsoid. Do I dare try to draw it inside here? I don't know. You get the idea. So anyway, there's these nested ellipsoids, one inside the other. And what we're going to show is that, you know, we start at some value of v. We're on some ellipsoid. And as time goes on, we keep going to smaller and smaller values of v, which means not necessarily that we're going radially inward. We might be wandering around, but we're generally going down to smaller and smaller ellipsoids, and hence approaching the origin. Do you have a question? What does a level set mean? It's a set where v equals a constant. A level set, yeah, meaning v equals constant. Sometimes called a contour. Yeah. Any other question? Yes?
I'm a little bit confused. So do you mean the trajectory is approaching the center origin, or is the capsule approaching?
The question was, if I understand you, is it that the trajectory is approaching the origin or that the ellipsoid is approaching the origin? So the ellipsoids, just think of as ways of partitioning the space into these level sets of this function. The ellipsoids aren't going anywhere. They're just like imaginary surfaces sitting there in the space. The trajectory is what's approaching the origin. And we can see that because we can, like, think of it this way. At each moment, we could ask the trajectory, what level of v are you at right now? And then it will just figure out which ellipse it's on. It says, I'm at v equals 12. Then you watch it a little later. Now it's at v equals 10. So it just tells you it's moving in. And we don't care about many details beyond that. Anything else? All right, so then the idea of the proof, of course, if we want to show that v is decreasing, whoops, that's the wrong board, is that we're going to calculate rate of change of v. And we want to show that dv dt is less than 0. That is, we're just decreasing in v. If r is less than 1, we're going to need that assumption. And also if we're not at the origin. Once you're at the origin, remember the origin is a fixed point, so v won't be decreasing there. It'll just be dv dt is 0. V will not change once you get to the origin. But so as the geometry showed, the trajectory, that means the trajectory is reaching smaller and smaller ellipsoids, and hence, by the form of the functional form of those ellipsoids, that means x, y, z has to go to 0. Okay, so let's calculate here dv dt, and you'll now see why did we choose this v. It's because of beautiful properties that happen when we take this derivative. dv dt, actually it's convenient since differentiating x squared will produce a factor of 2. Let's rather calculate 1/2 dv dt to get rid of all those annoying 2's. Then we'll get xx dot over sigma from differentiating the 1 over sigma x squared term, where there's a chain rule. Don't forget the chain rule factor. We're not just differentiating with respect to x, we're differentiating with respect to t. So when you differentiate x squared, you get 2x x dot, and then we've divided by 2. Likewise, when we differentiate the y squared, we get y dot, and then plus z dot. And here we next substitute the Lorenz equations for x dot, y dot, and z dot. So this becomes, after you plug in for x dot, Well, let's see. Should we remind ourselves what the equations are? So their x dot is, I always need reminding, actually. Shouldn't admit that. Sigma y minus x. That's what I was going to say. Okay. Y dot is rx minus y minus xz. And z dot is xy minus bz. That's the Lorenz system. And so now when we plug in, notice this factor of sigma in x dot. That's why we have the sigma in the Lyapunov function, to cancel that sigma out. So the 1 over sigma x dot term, this times x, becomes yx minus x squared is the first term. Yy dot gives us ryx minus y squared minus xzy. And the last term, zz dot, gives us zxy minus bz squared. And now stare at that, see if you can cancel anything out. You can see here's an xyz term that cancels with this one. So that's good. And let's clean it up a little. Then we get that this boils down to r plus 1 xy minus x squared minus y squared minus bz squared. So look at that last expression and ask yourself, can we be sure that it's negative? Well, okay, what could cause trouble? I mean, this is a negative of a constant parameter. Remember, b and r are both positive. So this is definitely negative. I mean, if z equals 0, it could be 0. Likewise, this is less than or equal to 0. So is that. However, this term could cause trouble, right? Because if x and y have the same sign, then this will be positive, if they're both positive or both negative. So it isn't totally obvious that this expression is, so to speak, negative definite in the language of linear algebra. But it is. And you can see that if you complete the square. So complete the square in the first two terms of this. So if you complete the square in the first two terms, by that I mean we're going to regard this xy as a middle term in some binomial that's being squared. Then you can write it as, let's see, so still continuing with our expression for 1/2 dv dt. Completing the square in the first two terms gives me minus the quantity x minus r plus 1 over 2 times y, all squared. Right? So think about that. What do we have here? When you square it out, you'd get minus an x squared minus 2 times, and well, with the negative sign will be plus. So 2x r plus 1 y over 2. That is this mixed term here. So that's working. But then we've also created a new term, r plus 1 over 2 times y all squared, which has to be then subtracted off to keep things equal to what they were before. So that then enters this y squared term and gives us now minus 1 plus r plus 1 over 2, this compensating term here, squared, all times y squared. And finally, the minus bz squared, which is just off on its own. So check that algebra if you had any trouble following that. But if you just expand this out, you'll see that it's the same expression as what we had before. And now I claim it is actually easy to see that this is strictly negative. So why is that? I mean, well, it's a negative something squared minus, we have to think about the sign of this coefficient. Actually, I screwed that up. Thank you. If you notice that it was wrong, this is a minus here. There, now it's better. We have to check the sign of this big parentheses, but it's negative, it's minus something. Now, let's actually, while we're here, let's look. what's going on in this big parentheses? It's 1 minus something. But we said r is less than 1. Right? We're in the region where r is less than 1. That means the numerator is less than 2, which means this little parentheses is less than 1. Squaring it, it's still less than 1. And 1 minus that then is positive. So we have a positive expression in this big parentheses because r is less than 1. And so we have a positive thing times y squared, a negative of something else squared, and a negative positive number times z squared. So this whole expression is definitely less than or equal to 0. Right? That's clear, I think. You would agree. The only issue is, where here we did absolutely use the fact that r is, or the assumption that r is less than 1. Now, let's go a little bit farther and ask, okay, it's definitely not positive. Could it be 0? You have to check that too. Is there some place where it could be 0? Well, let's think about that. When could it, meaning this expression, equal 0? Well, if you have a negative sum of squares equaling 0, it's going to require that each term is separately 0. Like here, I mean, this expression is negative except when z equals 0. So we need z equals 0 to get this equal to 0. And then likewise, since this prefactor is not 0, it's positive, for this term to, I mean, since the whole thing is 0, we're going to have y equals 0 also. And then finally, looking back at this expression, if y is 0, now we just have minus x squared. And so for that to be 0, you need x equals 0. And so the only place that this expression is 0 is when all three variables are 0, meaning you have to be at the origin. There's no other place. So think about that if you didn't quite get the details there. But the claim is just what I said over here, that if we're at r less than 1 and we're not at the origin, dv dt is strictly negative, meaning we are going down to smaller and smaller ellipsoids. And then, since v is bounded below by 0, and we're monotonically decreasing in v, that can be used to show that v of x of t, y of t, z of t since it's strictly decreasing and bounded below by 0, it has to go to 0. It can't asymptote to something that's positive, because at any place where it's positive, v dot will still be negative. It can't actually asymptote there. It's still going down. So since v goes to 0, then the only place where the function v is 0 is at x, y, z equals 0. So this is what we wanted to show, that x of t, y of t, and z of t, I mean, in other words, the trajectory is approaching the origin as t goes to infinity. So that was the claim, and that's the argument. Any question about this? Yes?
Could there be some Zeno paradox kind of case that v is negative, dv dt is negative, but yet it goes infinitely slowly?
The question was, could there be some kind of Zeno's paradox phenomenon where v is decreasing all the time but somehow doesn't go to 0?
Yeah.
So you have to think about what that would mean. I mean, in order for it to be decreasing as a function of time and then asymptotically approaching something, what is it approaching as a function of time? Is it approaching 0 or not? If it is approaching 0, we're done. That's what I'm claiming. So you must be claiming it's not approaching 0. That's what you're worried about. So then that means it's bounded below by something else. And that's not going to be possible, because at any place above the level v equals 0, dv dt is, well, I guess that's what you're worried about. You're saying that this could just kind of like go asymptotically out to infinity, and meanwhile its dv dt was negative the whole time, but it didn't asymptotically approach 0. But that, I don't think that's going to be possible, because that would mean that this v is approaching v dot equals 0, but v dot equals 0 only occurs at the origin. I mean, in other words, we would have to think about what's the prediction for v dot along this supposed asymptote. It would have to be 0 there, but it can't be because the only place where it's 0 is down here. So that's the problem. Is there another question? Yes? Oh, how did we choose the Lyapunov function is a good question. That's ingenuity. That's like asking how do you choose that G in the Dulac criterion. It's the same thing. You don't have a systematic way of finding Lyapunov functions. You just have to be algebraically clever. And here the cleverness was to stare at this and try to figure, I mean, okay, you want something that's a positive definite expression like that V, that is to say it's positive everywhere except at the origin. And a sum of squares is a good guess for a positive definite thing. And so if you just naively tried x squared plus y squared plus z squared, which would be saying that the, you're just monotonically changing, your distance from the origin is shrinking. That turns out not to be true. It's not that the distance is shrinking. You need that factor of sigma in there to deal with this, this term. I think you can probably show that there might be places where the distance increases, yet you're still moving to an inner ellipsoid. Anyway, I don't have a good answer for you. You just have to you have to monkey around and try some things. And there are many problems actually in applied math that are unsolved to this day because nobody has been able to find the right Lyapunov function. Like we sort of believe that in pipe flow, in turbulence, below a Reynolds number of, I don't know, like say 800 or something, that the only solution that is stable is the laminar solution. Yeah, that the system it will have a global attractor that's laminar. But I don't think anyone has proven that. But we kind of know it's true, but nobody has found the Lyapunov function to prove it. Anyway, so, okay, let's leave this. And all right, so now let's dispense with this boring region where r is less than 1 and not much can really happen. And talk about what happens when r is bigger than 1. So next, let's suppose r is greater than 1. Then we already discussed in the last lecture that the origin is a saddle in that case. And we also showed that we created two new fixed points that we called C plus and C minus. And so those two new fixed points newly created out of the origin when r was 1, you could ask, what about those new fixed points? Those corresponded, remember, to steady rotation of the water wheel in either direction, or of this convection cell that the model is supposed to describe. Are those states stable? Well, they are at first. And the calculation of that is left as a homework exercise for you. By the way, the homework, I mean, you must have realized I'm not collecting today. It's now due after our vacation. Yes, shucks. So there you go. Anyway, so these points are linearly stable, you'll find. You'll get that by actually just calculating the eigenvalues or some conditions on the eigenvalues for this three-dimensional system, that they're linearly stable points in the range where r is greater than 1, but less than some other number, which turns out to be sigma times sigma plus b plus 3 over sigma minus b minus 1. And I'm going to call that number r sub Hopf because it will turn out that a Hopf bifurcation occurs at that number. In deriving this, you're also going to have to assume that the denominator is positive. That is, we're assuming sigma is greater than b plus 1, which for Lorenz's values, you may remember that Lorenz studies sigma equals 10, b equals 8/3. Actually, I need to put the Lorenz paper on the website, so let me do that today. Anyway, that is the regime that we're in. So anyway, here's this exercise, and for his values, the sigma equals 10, b equals 8/3, our Hopf will turn out to be, or maybe I'll just write it r sub h sometimes. That will come out to be about 24 point, if I recall, 24.74. So there's a pretty good range between 1 and around 24 something where these fixed points are stable. All right, and so you can go to them in that range. Now, what would happen when r is greater than r Hopf? There's more to say about those fixed points. Maybe you should look at the book to see exactly what they're like, but I'm going to show some simulations in a few minutes, and those will show you too. But so moving now, increasing our knob, now let's move r greater than r Hopf. What will happen? Well, it depends what kind of Hopf bifurcation it is. That is, at a Hopf bifurcation, there's a limit cycle that has been created, but is it a stable cycle, in which case it was a supercritical Hopf, or was it an unstable cycle, in which case it existed below RH and was unstable? Well, so I don't know, you want to guess if you haven't read the book already? I think you might sort of suppose that since it's, I don't know, maybe you have an instinct. You might suppose, maybe you wouldn't, but you might suppose that there exists a small stable limit cycle. That is, you might guess that it's supercritical. A small stable cycle around C plus and C minus. Each, one stable cycle around each of them. That is, because remember, solutions come in pairs, symmetrical pairs for the system. Well, that's not what happens. That is not the case. Actually, the bifurcation is subcritical. So actually, no. For the standard Lorenz parameter values, the bifurcation turns out to be subcritical. Which, remember, that was the day I was flapping my arms around saying, you know, subcritical is dangerous. Subcritical means that there's no attractor nearby. So let me draw a little picture. This is a difficult calculation, by the way. For years, people in the field weren't sure whether it was sub or supercritical. They didn't have a proof. And it was complicated to do it correctly, and it kept being done wrong. And then finally, it was resolved in a book by Marsden and McCracken, which I refer to in my book, and you could read their proof there. So it really is subcritical through a pretty elaborate calculation. So what does it all mean? Since it's subcritical, trajectories must jump to a distant attractor. I mean, that's what makes it dangerous. There's some discontinuous behavior happening. Must jump to a different attractor than C plus or C minus. And what is it? So remember, I had mentioned that we were taking the Sherlock Holmes philosophy of ruling out everything that was impossible, and then whatever is left, however improbable, must be the case. So what have we ruled out? Here's a summary of what we know so far. That as a function of r, so this is kind of a schematic summary. Don't really ask me what's the vertical axis in this diagram. The horizontal axis is r. So we know that r equals 0 that the origin is stable. So I'm trying to indicate the origin by this line. That's like, think of this as you want, you know, this is the origin here. Then as we increase our value of r, at some point we give birth to these 2 points, C plus and C minus. We know that they really live in 3 dimensions, but I'm just trying to draw a simple diagram on the board. So that's why I'm drawing this schematically. Think of this as C plus and C minus having bifurcated off. The origin is now unstable. We showed that this happened at r equals 1. Then they remain, you know, perfectly okay until we get to this place that we were calling r Hopf. And at r Hopf, I claimed, but didn't prove, but hopefully you'll believe me, that there are these subcritical Hopf bifurcations. So that would mean that there's backward bending, unstable cycles coming out of those points, rendering them unstable. And if you want to indicate that these are really sort of cycles, you may want to draw some kind of bowl-shaped thing here. You don't have to, whatever. But, you know, and those go back farther and farther. Like this and like this. That actually, you may be imagining something here. You may imagine that these bowls somehow hit the origin. The picture suggests that, doesn't it? They do, in fact. There's some value around, for the standard Lorenz parameters, if I recall, somewhere around 13 or 14, where these unstable cycles have grown so big that they actually touch the origin in a homoclinic bifurcation, and all kinds of mayhem breaks loose when that happens. So it's been referred to as a homoclinic explosion. If you read the book, there's a whole book on the Lorenz system called the Lorenz equations by Colin Sparrow, and he spends a lot of time talking about what happens when these cycles hit the origin and what are the implications of this homoclinic explosion. But it's pretty delicate, and I think it's best left to a more sophisticated course. It has to do with an object called the horseshoe, which I don't want to talk about here. So I'm just going to take a more naive point of view. Lorenz didn't know about any of this. He's just looking, you know, as he cranks up r, we pass r Hopf. Everything in sight now seems to be unstable, right? My old C plus and C minus, they're unstable. The origin is unstable. You could say, well, all right, so what can the trajectories do? Or they could escape to infinity, maybe. The whole system seems so unstable. Maybe they blow up. Well, no, that's not possible. That's another homework exercise, and not a hard one. That is, could the trajectories go to infinity? No. Could the trajectories escape to infinity? No, that's not a difficult thing to prove. You can show that there's a big sphere that has the property that all trajectories outside that sphere move toward the sphere and eventually enter it and never get out. That is, there's a trapping region. Everything eventually gets trapped inside a certain big sphere. And so I'll walk you through that calculation on the homework. But anyway, so that's an easy calculation. And Lorenz does it in his paper, too. So trajectories are not getting out to infinity. There are no attractors in sight. There's one other possibility you could think of, or actually maybe two. What about a stable limit cycle somewhere else? I mean, it doesn't have to have bifurcated from C plus or C minus. Maybe we just have some stable limit cycles that are born out of the vacuum, you know, like in a stable, in a saddle node bifurcation of cycles. Well, that's a delicate question, too. Lorenz gave an argument that there are no stable limit cycles for his system. I'll discuss that later. I don't want to do it now. But he argued pretty persuasively that there are no stable cycles for r, you know, at least immediately greater than, actually, for r equal to the value he used. which was r equals 28. That's the one I want to look at next. What happens when, I mean, that's what he picked. That's sort of out here. So this was supposed to be r Hopf. Whoops. Right there. 28 is around here. Okay. One last thought. If there are no stable cycles, you could imagine maybe you asymptotically approach an invariant torus. Maybe there's quasi-periodic motion on a torus. We talked about quasi-periodicity. Well, that's impossible too. That's an easy argument. So could the trajectories settle into quasi-periodic behavior on an invariant torus? By invariant torus, what I mean is that once you start on that torus, you'll stay on that torus forever. So could the trajectories approach such a torus, sitting in the three-dimensional phase space, and just be winding around, never getting off? Well, no. And the argument is easy, that if there's an invariant torus, then think about the volume inside that torus. There's a solid inner torus, and that solid in there has some volume, and since the surface is invariant by assumption, the volume of all those points inside will also be invariant. And that's impossible because we know that volume shrinks exponentially fast for any region in the Lorenz system. We discussed that last time. So there can't be any invariant tori because they would violate the volume contraction that occurs in this system. So now we really have eliminated everything we know. And Lorenz came up with this argument and then did his, I don't know what the order was, but anyway, he did numerical integration of the differential equations to see what would happen, and I guess I want to do that now ourselves. Is there any question before we start turning on the computer? Yes?
When you say argue, does that mean like you actually proved it, or is it?
No, so it's a very good question. The question is, when I say Lorenz argued, did he actually prove it? No, he did not. He didn't actually prove it. He didn't have a proof that there were that stable limit cycles were ruled out. He gave evidence. I'll show you his argument. It's not a proof. There's a gap, and it wouldn't qualify as a proof. There's a gap in it. Oh yes, you're full of good questions. Yes. What do we know today? Right. It's now more than 50 years since his paper. And we do know for a fact that there is a strange attractor. But we only learned it in the past few years. It was proved by a young guy named Warwick Tucker. And in the first edition of my book, it was not known at that time. So in the book, I make a big point about how we still don't know. But now we do know. So yes, Warwick Tucker proved that there really is a strange attractor, as we're about to see. And it was a pretty hard argument. Pretty much everyone believed it, but it wasn't a proof. Is there another question? Yes?
So, the definition of an invariant torus volume is such that every point basically evolves to a point in that same volume. So, by volume contraction, why can't the volume inside the torus shrink into another invariant torus?
Okay, the question is, think about the torus, and it's got its surface, and then it's got all the points inside. Couldn't we just have it that the points inside the surface of the torus, they're doing volume contraction, but what's happening to the surface? It's not contracting, right? I mean, the surface is invariant. So the volume of that torus is invariant. That is the closed torus, surface plus inside. That's an invariant volume. And the inner part can't detach from the surface. That would cause discontinuities that don't happen in this flow. But the point is that the solid torus is an invariant object, surface plus interior, as well as that the surface is invariant also. Yeah. Okay. So let me stop delaying and put down the shades here and show you some simulations if they work. There's always a question. And I should turn on the screen here, which is blank at the moment. Now it's not blank. Good. Mr. Projection Man, should I make it darker, or do you think it'll be good like this? I can go a little darker. I could go like that, or really dark. You think it's good this way? Okay, fine. So let's first show you where I'm getting this software. So if you Google or Bing or however you like to do it, interactive differential equations, the first thing that will pop up is this site, and that's where you want to go if you want to reproduce what I'm about to show. And so, except since I had some Java security issues, I'm not going to try going in that way. I've already gone in this way, and it was okay. So let me show you a few things. Here's what these are is lots of little Java applets. You basically can't do anything wrong. You just click them and they'll, there's very little room for error or even creativity. So like if I click on this one, what we're showing here is essentially doing the experiment that Lorenz himself did, where he started with okay, what are you watching? This is time running horizontally and x vertically. We've got his standard parameter values. They're all listed here. They're too small for you to see probably, but 10, 8/3, and 28. And then we're going to do two initial conditions. One in yellow, which has 6 digits of precision. Lorenz at the time was doing his calculations on an old machine called the Royal McBee. That was a kind of a mechanical. It was fancy, actually. He had it in his office, which was unprecedented. And I mean, he had his own computer. That was crazy. People had computers. You had to go to a computer center and put punch cards in there. And no, he had his own machine. And so he could do things to 6 digits in there. And so the yellow curves are the 6-digit calculations. And then Lorenz tells this dramatic story about how he wanted to rerun a calculation, and he wrote down the initial condition, but to save time, he only wrote 3 digits instead of 6. And when he reran it, it tracked the old result for a while, but then it diverged. And he thought there was something wrong with the machine, which was common because frequently vacuum tubes would blow out, or there would be literally bugs in the machine and stuff like that. And so he learned, how to fix it, and he also would call the technician in to do whatever. But the problem wouldn't go away, and then he realized it had to do with that he truncated 6 digits to 3 digits, and it made a big difference. So you're going to see both the 3-digit and the 6-digit simulations. Here's the 6-digit one. And so you're seeing x as a function of time. It sort of does something simple for a while, then it does something that looks kind of chaotic. Now here is the 3-digit simulation. Notice it's not tracking on top. It did for a while. I mean, it started at where this red line is. I've started the blue by truncating the yellow. This said 13.356991. I truncated to 13.357. But that's the only change. And you can see that it sort of immediately starts diverging. And it was not a special property of that initial condition. We could do something over here. You see the same pattern. You start somewhere. First you have these growing spirals. Then they start to do something crazy. And there, the blue is sort of tracking the yellow for a while, but then it diverges and does its own crazy thing. And so in trying to understand that, Lorenz was led to the idea that maybe he should do, like we draw things in phase space in 2 dimensions, well, he should do a 3-dimensional phase space. That was not really possible with the computer graphics in 1963, but he could do various projections onto 2 dimensions. And so let me show you what some of those look like. If we jump back out, let's call it phase plane, although it's not really a plane, because you know it's a 3D space. But we'll do this projection. Now, one thing that's kind of nice about these applets, which I should say were written not by me, but by Hubert Hone, who was a teacher of computer graphics at Massachusetts College of Art. So when I used to teach at MIT, there would be this guy sitting in the front who I didn't recognize, who had a beard. And I actually thought he was a homeless person, because we used to have homeless people coming in frequently to attend lectures or just get out of the cold. And so it was not unusual to not recognize students. It turned out he didn't know any calculus, which was interesting that he was taking the course not knowing calculus. But he found that he didn't need to know calculus because he was so good at computers that he could just solve every problem on the computer. You know, he knew how to do numerical integration. And so he made all these little applets for himself to teach himself the course. And eventually he showed them to me, and I realized he's a very interesting guy, this guy. And so I thought his stuff was beautiful because they're very artistically rendered, as you'll see. And we did sort of the whole differential equations course using his applets. And we thought we would get rich, but in fact the publisher's giving it away free, as you could see on the web. So we did not get rich. But mankind has benefited through Hubert Hone. Anyway, so what you're going to see here is I can start somewhere in this little phase plane. And let me just hit the pause button for a second. There's a lot going on. Here's a projection in the, well, let's see, I guess it's the XY plane. And this is supposed to represent a little blob of fluid where it's hot down here, see it's red, and cold up there. Remember I talked about convection, that if you had hot ground and colder upper atmosphere, then a blob of air would tend to rise. And so you're watching this representative blob of air rising and cooling. And let me clear the screen and let you watch again. See, this thing is rotating around. There's the convection cell. And meanwhile, we're spiraling in the phase plane. Now, this is going to start reversing. See how that's got irregular reversals? That's sort of like what the water wheel did. You can clear the transients to watch what's happening from where I stopped. Meanwhile, there are also time series running. So what you're seeing in the time series they're color-coded. So I guess we've got X in yellow, we've got Y in red, and Z in green. And you're now observing what chaos looks like in this system. So if we just continue, let me let it start again. Focus on the phase plane picture again, or the phase portrait. This is what motion looks like on the strange attractor. That there's a dot that goes around one of these fixed points. These gray fixed points in the middle are C plus and C minus. So you kind of go near them, but they're unstable, so you spiral away, and you spiral away until you get so far away that you jump to the other one. Maybe I'll see if I can show that by clearing and starting near a fixed point. See how I spiral away from it, then jump to the other side, spiral away from it, then jump back. You can also do other projections here. So you can click this button for the XZ projection, and that makes it look like a butterfly. Now, you've probably heard of the butterfly effect, and it's just a weird coincidence that the attractor looks kind of like a butterfly in this projection, and that when Lorenz gave a famous talk about what he had discovered, he gave this metaphor about the butterfly flapping its wings in Brazil that created a tornado in Texas, you know, years later by changing, or months later, by changing the air currents a little bit and changing the weather. They're still looking for that butterfly. There are also butterflies that prevented hurricanes, but we'd never, you know, never found them either. Okay, so anyway, that's one other projection. Then there's, I guess, one last one that you might find interesting. This is the projection that Lorenz shows in his paper. This is y against z. And anyway, I hope, excuse me, you're now getting a kind of visceral feel for what the motion is like in this system. And so the idea is that there's this underlying set that the trajectories live on. That's the strange attractor. Is there any question about what you're seeing? Comment or anything? Yes, please, in the back. Yep. Right, the system is symmetric in x and y. The question was, this system has a symmetry where xy goes to minus x minus y. Can we have chaotic systems without that symmetry? Yes, there were ones discovered afterward that are in effect like one of the wings of the butterfly. So we'll discuss that attractor later, called the Rustler attractor. It's very similar, but it's effectively like half of this system. And in fact, it only has one nonlinear term, whereas Lorenz has two. The symmetry is not really important to the effect. Yeah?
So last class we talked about how all of the trajectories, the volume of all of the trajectories kind of compresses down. Is that something that we can see in some way?
The question was, can we see the volume contraction in here? You can't really see it very well because everything has been pressed onto a plane. But what you could see, and maybe next time I'll bring a model of the Lorenz attractor that's a three-dimensional model that was made with 3D printing. So one year the students gave me a 3D printed Lorenz attractor as a present, and I love it. So I still have it, and it's, you know, as you move it around, you'll get a feeling for what the attractor is like. And you'll see that it's very flat. It reminds you, or reminds me of a mask, you know, that you wear at one of those parties where they're just the two eye holes. And so it's sort of like that, but it's a little bit twisted, and it's actually not a surface, as we're going to discuss later. It's really like many sheets of surfaces all packed together. Very hard to perceive the space between them, but there is space between them. Yes?
You still haven't talked about how we got to the Lorenz, how Lorenz got to the Lorenz. Did he like come through from a water wheel?
Okay, this is a good question too. So the question was, how did Lorenz actually get to the Lorenz equations? Was it from the water wheel? No, it was not. The water wheel came after the Lorenz equations in an attempt to understand it mechanically. Okay, let me take just a minute, because it's an interesting, really interesting history. How did he get to them? And then I guess I do want to go back to the computer too. Okay, well, so Lorenz was interested in the weather. He had worked in, he was a math major, I think, in college. I think he went to Dartmouth. He went into the war in World War II. He worked for the Army in weather forecasting, which, you know, is important for military operations. Are you going to launch an attack on a day when it's bad weather or good weather? You need to think about that. Anyway, so he knew a lot about weather forecasting, and there was a controversy in the 50s about what's the best way to do weather forecasting, given how difficult it is. And so there were three types of approaches, which were one is sort of like you try to find weather based on thinking about precursors. You could ask, what was the weather like yesterday? And then you look over historical records and see when was it most like yesterday and what happened then. Okay, so you could do pattern matching like that. Or you could say that the way to predict the weather is through linear regression. So the second method was, just to kind of caricature it, but the idea is something like this. To figure out the weather here in Ithaca tomorrow, I need to take the temperature in St. Louis at 9 o'clock yesterday times 0.1 plus the barometric pressure in Cleveland times 0.04. You know, like some ridiculous thing where you're making a linear combination of all kinds of variables that you might think are relevant, and you make a gigantic statistical model and you fit the coefficients. And maybe it will work, okay? So some people are trying to do it that way. And then a third way is you say, no, we know the laws of motion of the atmosphere. We can do this with fluid dynamics and just think about the motion of the air and the pressure over the ocean and all that other stuff. Well, that would be the physics way of doing it, but the trouble is you would need gigantic computers and very well-resolved measurements of the atmosphere, and the computers in the 1960s weren't good enough to do that. So those were the three methods, and that was the raging discussion. What's the best way? Now, what Lorenz did was very interesting. He wanted to test the statistical method versus the pattern method, and to do it, he wanted to test it in a computer, and he wanted artificial weather. Okay, he wanted weather in the computer, something that was weather-like. He couldn't deal with real weather, it was too hard. So he tried to make something that was unpredictable, like the weather, but deterministic, so he could solve differential equations. And so, you know, the story's often told, like Lorenz blundered across the Lorenz equations. That's not true at all. He was very deliberately trying to create an unpredictable, deterministic system. And he talked to a colleague of his who had said that he was aware of such a system in a model of convection, but it had 12 differential equations in it. And they were discussing it, and eventually they sort of boiled it down to, and I think mostly Lorenz, boiled it down to 3 that seemed to be at the heart of this 12-dimensional thing. And so that was why he was led to it. I mean, he was really looking for something that would be deterministic but not periodic and unpredictable. And then that he would use to test these weather models. But it ended up being more interesting than anything about the weather models. And when he saw this funny thing about the truncation causing unpredictability, he realized he had gold there. And so then he tried to convince his colleagues that this was great, but most of them didn't see the point because they said, that's a lousy model of convection. It's way too reduced. You know, the weather is not like this at all. And he knew that, but it took them a long time to catch up to what he had discovered. So that's a long answer, but that's approximately the story. So anyway, back to our simulations. Let's talk about what's chaotic or unpredictable about this. And so to do that, I want to jump back out and go to, by the way, if you want to explore a little bit on your own, before I show you the unpredictability aspect, this is a pretty handy little program. It lets you change the parameter values, like here's the R, as a slider, and it's currently set at 28. But I can, you know, just move it up to something else I'm interested in, like, and you can see the numbers are changing on the top. Maybe you can't see on the camera there, but there's an indication of what I'm at. So like, let me jump to, I don't know, you want to suggest a number between 0 and 320? 157. Okay. So I dial in 157, there it is, dink, and let it go. And then it'll do something. Now, there's transient behavior, so if I clear that, isn't it interesting, you know, you've picked something where it has a stable limit cycle. And it has a fairly complicated stable limit cycle that's looping around like that. And you might say, well, wait a second, the system has a symmetry. It should have a symmetric version of that stable limit cycle. So maybe it does. What if I click over here? No, I got that one again. Try over here. Same one. Oh, wait, I'm in the X, Y projection. Maybe let me see if it's clearer in this projection. Clear the transients. Oh, I see. Maybe this is a limit cycle that obeys that symmetry. So its symmetric partner is itself. I have a, right? I mean, that looks pretty symmetrical. So it does just, you might have thought as you increase R past 28, you're just going to get increasingly complicated chaos. That's not true. You get chaos, and then you suddenly go back to these funny limit cycles, and then you get more chaos. It's very intricate what goes on there. So you can explore some of that with this program. But anyway, now back to what's unpredictable. Let's look at this representation. That's sensitive dependence. So what I'm going to show next is you'll see a quick sketch of the attractor in gray, and then you're watching some kind of trajectory moving on there. Now notice it's become kind of dumbbell-like. That is, it has 2 points on it, a red dot and a yellow dot. And so what we're doing is we started 2 initial conditions very close together, one red and one yellow. But you couldn't see their difference at first because they were so close together. So watch again. I'll just run it for a short time. And I'll pause. That's actually 2 initial conditions. what looks like one yellow dot on the attractor. But what's being shown here in the numbers is that they were the same, except that there was a distance between them of, it actually says 10 to the minus 40th. I don't think that's true. We probably didn't make them that close. That's kind of funny. But anyway, they were close together. And after a certain amount of time, they will diverge from each other. So let's continue. Now they have started to visibly diverge from each other. And if you watch their time series, you'll be able to see that the yellow dots and the orange dots are actually no longer on top of each other. You sure that's clear on the camera? Yeah? Okay. I mean, because I feel really tempted to just go like that. Isn't that better for you guys in the class? Can you still film like that? Okay. Maybe I just want to show it like that for a second, because it looks very hard to see in the room. Let me start that again. So watch, a yellow and a reddish orangey trajectory. See, they've diverged. And now you can see this bar running around crazily on the attractor. And what that means is that although the 2 points started, they started on top of each other, and everything was sort of predictable for a while. That is, even though there were slightly different initial conditions, they still follow the same track, complicated but predictable track. But after a while, the red and orange dots are totally decorrelated. They're on separate parts of the attractor. Sometimes they come close together. The bar is small. Sometimes they're very far apart, almost like diametrically opposed. So we want to quantify that by looking at the separation between the trajectories as a function of time. And that's what we can do here by clicking on this button, which says delta divergence. So let me just start somewhere. And they're sort of staying together. And then they start visibly diverging. So if I pause, here's what's being shown. On this little time series graph, I'm showing the logarithm of the separation between them. The reason I'm showing the logarithm is because there's reason to believe that there's going to be approximately exponentially fast separation. So if I take the log, then I should get something that looks kind of like a straight line growing in time, and then eventually saturating when they're about as far apart as the attractor will permit. So let me try that again. Let me start somewhere. Watch from the beginning. Okay, we started down here at 10 to the minus 7. And then this line is something of order 1 when they're now about as far apart as they can get. And so if I, whoops, so let me keep going. Sorry, now they're just far apart. There's nothing to watch. I want to watch the initial transient, so let me start that again. Okay, so they've now pretty much saturated. So will you sort of believe me if I say that there's a straight line that goes through these dots? It's not very straight and convincing, right? But it's also kind of, there's a suggestion of some line through this beginning part, as we went from 10 to the minus 7 up to order 1. So if you sort of buy that there's a trend line sloping up through here, that's what we mean when we say trajectories diverge exponentially fast. It's not beautifully convincing, but it's sort of there. So I want to write that on the board just to record it for you. Do you want to ask anything before I turn off the computer? Yes? I don't have a 3D of this. There may be other software on the web. One of our students has posted something on Piazza. I don't know. It might do something. I don't know. Does that one do that? Yeah. Okay. So you can take a look at the Piazza site and try this in 3D. Yes? This is a very good question. What is the rate of separation for trajectories if you are trying to predict the weather? Yes, absolutely right. I need to discuss that because that's an important issue in quantifying chaos. So that rate of separation is a property of the system itself, in this case of the weather. And people do know what this quantity is called. There's a concept of a predictability horizon. How far out can you predict a chaotic system? And it depends. So in the case of the weather, I don't actually know what the best estimate of the number is. I think it's considered to be on the order of a week or two. 10 days. Okay, are you in this subject? 10 days, yeah, okay, yeah. So, I mean, I think nobody at the moment feels you can predict the weather a month in advance, but everyone agrees you can pretty well predict it tomorrow. So it's on the scale of, like you say, about 10 days maybe. And so like the solar system, the whole solar system has been shown to be chaotic, which might surprise you because you think, man, that's really predictable. That's the clockwork universe. Well, yes, the time scale for the chaos is very long. It's got a predictability horizon of about 5 million years. So it's not forever. It's chaotic on the time scale of 5 million years, but for, you know, like Halley's Comet that returns every, whatever, 80 or 90 years or something, it's very predictable on that time scale. What about the solar system is chaotic on this time scale of 50 million years? So you have to look at the papers by a guy named Jacques Lascar or Jack Wisdom who have written about this. But I think it would mean, you know, like if you imagine the configuration of the planets as a whole at one time, and then predict out 10 million years where they're going to be, and compare that to what you would get if you just nudged one of the planets a little bit and predict out again 10 million years, you'll see that after 10 million years, there's a significant discrepancy between those two predictions. But it hasn't become, it's just like here with this bar, it hasn't become noticeable until a certain amount of time. So let me start writing some stuff on the board. I want to say more about all this a little more precisely. Okay, so the screen can go up. And the shades can go up. Oop. Later in the course, we'll see an example of an electronic circuit that's chaotic, but it has a time scale for its chaos of milliseconds. So, I mean, it really decorrelates very, very rapidly. And so this is an important concept. I mean, people think chaos is some kind of a fancy new word for randomness, but it's not that at all. It means that a system is deterministic and predictable for a short time, up to this predictability horizon, and after that it becomes unpredictable, effectively. So to quantify that, let's just talk about the Lorenz attractor again. As we just saw, on the Lorenz attractor, we were getting, if we call delta of t, this distance between the trajectories, it was sort of growing like whatever the initial distance was. So the notation here is something like this, that we're thinking of a trajectory. Here's x of t going through its three-dimensional space. And then here we had some nearby trajectory. And so this initial separation is delta 0. That is the length of that little bar there. And then as time goes on, there's going to be this much separation. And so this is x of t plus delta of t as a vector, and I just want to use the letter delta to mean the magnitude of this vector delta. This is delta here. This was x. So anyway, on the Lorenz attractor, delta grows like approximately delta 0 times e to the lambda t, where lambda is, and this is very rough as we saw, lambda turns out to be, for the standard parameter values, around 0.9. Just empirically when you measure it in the computer. Now keep in mind that what we saw in the computer was that when we graphed log of delta versus t, it looked very jaggedy, you know, and not convincingly straight, and then it sort of saturated. And so what I'm claiming is that this rough slope through here is that slope is the number that's around 0.9. So don't take the number too seriously, but there is some positive lambda. And so in that sense, the errors are growing exponentially fast. Then we get saturation after a while, because as you saw, the trajectories can't get any farther apart than the scale of the whole attractor. Okay, so this lambda is a concept called the Lyapunov exponent. And really, there are n Lyapunov exponents for an n-dimensional system. This is just the largest one. And this is the one that people talk about and call the Lyapunov exponent. But really what we should think about is for a given trajectory and a point on that trajectory, we should think of a little n-dimensional sphere of uncertainty around that trajectory's point. That sphere will grow into an ellipsoid as time goes on. And its longest axis, that is the one that's causing the fastest exponential separation, is the one that's growing at this rate e to the lambda t. And so let's not worry about the others. Anyway, having a positive Lyapunov exponent is considered a signature of chaos. You'll hear the phrase sensitive dependence on initial conditions. That means that small changes in initial conditions then get amplified exponentially fast. That's equivalent to saying positive Lyapunov exponent. Now, why that's important in terms of prediction, let me finish with this point, is let's think again schematically of, here's our system. We're thinking of two initial conditions right there, but you can't see them. They look like one because the difference between them is undetectable given our resolution. And they will stay basically on top of each other until we get to some time when you can start to see the separation between them. And so you would say that this system was kind of predictable up to about here. Let's suppose that we have some tolerance A. That is, by that I mean that when delta is greater than A, we can see the difference. Before that, we would say they're basically the same. Delta greater than A is when the deviation between the trajectories becomes noticeable or intolerable or whatever you want to call it. So, that's a question of your measuring instruments or what you care about. So you get to set A, or your instruments do. And then we can ask, how long is this chaotic system going to be predictable given that we have a tolerance of A? And you could reason it like this, that there was some initial deviation between them, delta 0. And so when delta 0 e to the lambda t becomes comparable to A, that's the amount of time after which you're going to say you can't really predict anymore. That is, they've started to diverge. So solving this little equation gives us a very basic, important conceptual formula, which is this. And this will help you understand what people mean when they say that chaotic systems are unpredictable, because it's more subtle than that. Solving that formula for t gives us t is around 1 over lambda natural log of A over delta 0. And you have to look at all the terms in here. What is this t? This t is the time that you can predict up to. So I'm going to call this the predictability horizon, or the Lyapunov time. And notice that it is of the order of 1 over lambda. So like when I said that the solar system had a Lyapunov time of 5 million years, I mean that the 1 over lambda is 5 million years. Now you could say, but wait a second, what about the logarithm? Well, it's kind of a rule of thumb in applied math that logarithms are all kind of order 1. Right? I mean, a number would have to be really big. Like, take Avogadro's number, a tremendous number, 10 to the 23rd. The log base 10 of that is only 23, which isn't that much bigger than 1. Really, I mean, okay. But anyway, a different way to put it is, suppose you say, this is unacceptable. We need to be able to predict not just 1 over lambda. We want to predict the weather 10 lambda out to 10 times longer than we currently can. Well, okay, you could do that. How could you do it? You could either make delta 0. I mean, basically, you'd want to make delta 0 much smaller. Right? People always say that. If I knew the initial conditions perfectly, couldn't I predict perfectly? Yes. Okay, yes. But you will never know the initial conditions perfectly because there's always uncertainty in your measuring instruments or whatever. So the real issue is, suppose you wanted to predict 10 times longer, and let's pretend that this natural log was a log base 10. They're not that different. Then to predict 10 times longer, you don't have to make your precision 10 times better. You have to make it 10 to the 10th times better. Do you get that? That's what kills you. That's what kills you. To make a factor of, say, 2 improvement, you have to get 100 times better in your precision. And to make a factor of 3, you need to be 1,000 times better. So it's this logarithm that is the big deal. And that logarithm, of course, comes from the exponential separation of trajectories. So that's the thing. You can never predict. I mean, you can sort of safely say, we'll never be able to predict the weather more than a few weeks in advance. Because to get just an extra week or 2 or 3, you're going to have to do 100 times better. I mean, eventually the logarithm will kill you. So, okay, maybe I will stop there. But you have homework to pick up.